Dear student, now I am going to deliver a lecture regarding the most fundamental study of the differential equation. Actually, the differential equation is of two types in nature. That is, first one is the ordinary differential equation. Most probably you have heard this name in your interclass. And the second one is the partial differential equation. So what do we mean by the ordinary differential equation? Ordinary differential equation means that if a dependent variable is dependent on only one independent variables, that is the differential equation involving the ordinary derivatives is called the ordinary differential equations. And the partial differential equation means the differential equation which contains the partial derivatives. That is, when a dependent variable is regarding the change of the independent variable which is in number 2 or more, that is the partial differential equation. So now I am going to introduce you that the differential equation are of many types. That means ordinary differential equation, there are so many things are there. That is, most fundamental thing is that the order and the derivative of the differential equation, because by knowing the order or the degree of the differential equation, we can classify the differential, which kind of differential equation is it and how do we solve it. Now let's start with the most simple one differential ordinary differential equation, that is first order linear differential equation. First order linear differential equation, that means linear means there is no product term between the derivatives and the dependent variable in the equation. Then the equation is called the linear differential equation. Now we are going to discuss our study in the sense, that is the ordinary differential equation of first order. It can be assumed that all the differential equation can be reduced to first order system of differential equations. That's why if we know the characteristic or the existence of the solution of the differential equation of first order, then we can generalize this for the nth order differential equation. Order, what do we mean by the order? Order is the highest order derivative involved in the differential equation is called the order of the differential equation, and the degree of the highest order involved in the differential equation is called the degree of the differential equation. Now we take the most simple one, this is first order first degree differential equation, and that's why I have told you that the first order differential equation provides the generalization of the nth order differential equation. So we need first whether the first order differential equation produce solutions or not, because the most rigorous study of the differential equation is related to the whether the differential equation provides solution or not. This is my topic which we are going to discuss. That is the existence and uniqueness of ordinary differential equation. I have told you the term that is ordinary differential equation, whether it is not. So now we are going to discuss the uniqueness and existence of the ordinary differential equation. Let's see the first order, first degree differential equation. And this is how do we proceed to yourself, how do you proceed to you, how the lecture is generated is like that. That is, first we know the differential equation, what type of differential equation, some examples of differential equation, and the existence and uniqueness discussion and conclusion. Now I have told you that we have taken the first order linear differential equation, that is dy dx equals to f of xy and y of x0 is y0. That means this is here y is the dependent variable and x is the independent variable, and f(x) is the function dependent on this, and dy dx is and the solution of the differential equation is prescribed under the initial condition, that is y of x0 equals to y0. What do we mean by the initial condition? Initial condition is that condition which is prescribed only one value of the independent variable. That means here x is the independent variable, and here we have chosen the first order differential equation. That means there is no question of the difference between the initial condition and the boundary condition. There are two conditions are there where the differential equation solution is prescribed under the condition. This is the first one is the initial condition, the second one is the boundary value condition. But here we are discussing the first order differential equation. That's why no need to discuss about the boundary value condition. But for your convenience, I am just telling you that there are two types of condition. First one is the initial value condition, and the second one is the boundary value condition. So what do we mean by the initial value condition? Initial value condition means if the condition prescribed in which the differential equation is to solve is that if it is prescribed only one prescribed value of the independent variable, and if the conditions are prescribed at more than one independent variable, then it is called boundary value problem. So now we are going to discuss about the existence. So now I am going to discuss the existence and uniqueness of the differential equation. Now I have told you that I have chosen the most simple, that is the dy dx equals to f of xy at the point y of x0 equals to y0. Now let us discuss some examples of differential equation of first order, which must be first order differential equation. I have as we are discussing about the first order differential equation, so the example should be the first order differential equation. These are the, let's see, first one, mod of dy dx plus mod of y equals to 0 at the point x0 y0 equals to 1, and the second one is dy dx equals to x y0 at the point 1, and the third one is here the number of equation is changed here, so there's nothing worried about it that. So this is that. Now if we want to solve these three differential equations under this initial condition, what can we get? The first one, obviously it is seen that the first one is not solvable. under this initial condition, because there is only one solution. Y0 equals to 0 is the only one solution at the point x equals to 0, but the given initial condition is differ from that. That is, no solution exists under this initial condition for the equation 2. Now if we solve this equation 3, that is dy dx equals to x, this is the most simple one. And if we take dy dx equals to x, then separable the variable separation method, we can get dy dx dy equals to x dx, and integrate. If we integrate, then y equals to half of x square plus c, which is the integrating constant. And if we evaluate, if we get the value of the integrating constant under this initial condition, we can get c equals to 1. C equals to 1. That means the solution of the differential equation would be y equal to half of x square plus 1. And the last one, if we take, you can solve it easily by variable separation method, that is dy by y minus 1 equal to dy dx by x. If we integrate this, then we can get y minus 1 equals to c into e to the power x, where c is the integrating constant. And just proceeding as before, if we put the initial condition of this differential equation, we get the value of the integrating constant. That is, we see that if we put this initial condition, this is an identity, zero identity, and this will provide us, there are so many solutions. So what we have seen from that, these three differential equation, first one gives no solution under this initial condition, second one gives the only one solution, y equal to half of x square plus 1, and third one gives many solutions, infinitely many solutions, because if we change c, then we get any solution. If we put c equals to 1, because c is independent here, so if we put c equals to 1, then we get another solution. If we put c equals to 2, we get another solution, and they have so many. So these three type of solution make a big question regarding the existence of the differential equation. If the differential equation exists, how many solutions it will provide? How many solutions it will give us? This is the most fundamental question. That's why I'm going to the further. So here we have seen that equation 2 has no solution at y equals to 0 equals to 1, and equation 3 has no one solution at y equals to 0 equals to 1, and equation 4 has infinitely many solutions. So the fundamental question is that I have told you that under what condition does the initial value problem has at least one solution, does the initial value problem has infinite solution, or does the initial value problem, IVP means initial value problem, has no solution. This is the most fundamental question here. To search the answer of this type of question, we go to the characteristic of the behavior of the fundamental behavior of the function of fx. We have chosen in the first equation 1, that is first equation 1. What is the first equation 1? That is the first equation 1. We have chosen dy dx equals to f of xy. So nature of f of xy is very fundamental regarding that. So what is this? That is, if this is most renowned mathematician Peano's have given this, that is dy dx equal to fx, this the initial value problem has a solution. That means if fxy is continuous in the domain R, then there exists at least one solution for the initial value problem 1. That means this is the known as most renowned mathematician Peano's theorem. What do we mean by the Peano's theorem? That is, if fxy is continuous in a certain domain, then the differential equation has a solution, then there exists a solution. So no question about that. Now our most fundamental question which we have raised in the before slides, that whether the solution unique or not. To discuss about that uniqueness, there is some nature of the fxy. That is, if fxy, this is known as the Picard's theorem, very well known Picard's theorem. What is this? That is, if dy dx equals to fxy, then if two conditions satisfied, first one is if fxy is continuous, this must should be, because the existence, this is the most fundamental existence one. If the differential equation have to produce solutions, then it should satisfy fxy, it is continuous. And the next one is the uniqueness. Regarding the uniqueness, what is this? It is if the partial derivative of f regarding y, that is del f del y, is continuous in the at that point, then we can say that by the help of the Picard's theorem, dy dx equals to fx has a unique solution. So this is the most important thing around regarding the uniqueness of the differential equation. So if these two conditions, that is first one is fxy is continuous in the domain and del f del y is continuous in the domain, then the differential equation dy dx equals to fxy under the given condition y of x0 equals to y0 has a unique solution. Okay, so we have got it. What do we have desired, that under what condition? But there are so many practical examples are there whether the determination of the partial derivatives continuity is very much harder than that. So we want to generalize, or we want to get some simpler one. What is that? This is the Lipschitz condition. What do we mean by the Lipschitz condition? By the help of Lipschitz condition, without getting the partial derivatives, we can say that whether the differential equation has unique solution or not. The Lipschitz condition. What do we mean by the Lipschitz condition? To get rid of from the harder mathematics engaged regarding the partial differential equation, we are going to the most simpler one, the Lipschitz condition, which is that this is a function fxy is said to satisfy Lipschitz condition in region D in xy plane if there exists a positive constant such that mod of f of xy2 minus mod of f of xy1 less or equal to k mod of y2 minus y1, where k is the positive constant, and fxy2 and fxy1 both lie in the region D. If this condition satisfied, this is called the Lipschitz condition. Lipschitz condition. So without getting the partial derivative, we can say about the uniqueness of the differential equation, which involves the functional form fxy, dy dx equal to fxy. So how do we use the Lipschitz condition to get uniqueness of the solution? This is the most fundamental existence and uniqueness of a differential equation theorem. This is the existence and uniqueness theorem. That is, first one is if fxy is continuous in D, this is must should be, because it is regarding the existence of the differential equation, whether it will decide whether the differential equation exists or not. And second one is regarding the uniqueness. In Picard's theorem, just we have changed by the continuity of the del f del y. we have changed that by the Lipschitz condition. If this Lipschitz condition holds in this plane, then we can say that there exists a unique solution about that. This is the existence and uniqueness. So if fxy is continuous in D and fxy satisfies the Lipschitz condition in a region D in xy plane, let x0, y0 be an interior point in the region and A be such that the rectangle R, x minus x0 less or equal to A, y minus y0 less or equal to B lies in D, and let M equal to maximum of this function fxy for xy in R and H is the minimum of this. Then there exists a unique solution of the initial value problem in the interval x minus x0 less or equal to H. It should be remembered that. Then the differential equation produce a unique solution in the range x minus x0 less than equals to H, where H is given here. So now let's see this example. Consider the initial value problem. Dy dx equals to y of 1/3 y to the power 1/3, the point is whether this initial value problem has a unique solution or not. First one, this is fxy equals to y to the power 1/3. Whether now it is a question whether the differential equation has a unique solution or not. First it should be, we can see that here we can see that fxy is continuous, so there exists a solution. Now if we differentiate partially with respect to y, then what will happen? This is del of del y, that is by 1/1/3. That means the power of y to the power 2/3 is minus. That is, we can't say about the continuity of the difference, continuity of that function, continuity of that partial derivative del f del y. So we can't say about the uniqueness of the differential equation, because these are the sufficient conditions, not necessary. As it is the sufficient condition to prove or to give us that if this holds, then we can say that, but if it doesn't hold, we can't say about that. That is the sufficiency condition. If fxy is continuous and the partial derivative of fxy with respect to y is continuous, then the differential equation has unique solution. There is no problem about that. But if one of these conditions doesn't hold, then we can't say about the uniqueness or existence about that, existence of the differential equation. That's why we can't say about that. But if we consider the second one, this is here dy dx equals to x mod of y, and the same problem arises here. What is that? Same problem is that del f del y, we can't say about the continuity of del f del y, because y mod y, this is the mod y function, and we can't say about the actually we know that if dy dx equals to mod x, fx equals to mod x, then this function is not derivable at the point x equals to 0. So this is not differentiable at the point y equals to 0. That's why we can't say about that. That means the Picard's theorem, the condition of the Picard's theorem doesn't hold here. So we can't say about the uniqueness of this differential equation with the help of the Picard's theorem. So that's why we are going to the second one, that is the we have lastly built up theorem regarding the existence and uniqueness on the base of the Lipschitz condition. What do we think about that? Here we see that for the second one, del f del y, dy dx equals to x mod of y. Here we see that the Lipschitz condition holds automatically here. Here we see that the Lipschitz condition holds here. So by the condition of the Lipschitz, as the Lipschitz condition holds, and this is the sufficient condition for the existence and uniqueness of the differential equation, we can say that the second one will have a unique solution. But if the first one, the dy dx equals to y to the power 1/3, we can't say about the uniqueness of that solution. So by the help of the Lipschitz condition, we can say that the second one produces the unique solution, but we can't say for that second one case that the differential equation has the solution which is unique or not with the help of the Picard's theorem. That's why I am telling you that the sufficiency condition, Lipschitz condition, is more powerful than the Picard's theorem. Is more powerful than the Picard's theorem. That means if we contrast the sufficient condition range, we can get bigger one. Okay, so this is the very most important achievement here, is that the Picard's, without fulfilling the condition of Picard's theorem, we can establish that by the help of the Lipschitz condition, the differential equation has a unique solution. So Lipschitz condition is more powerful than the continuity of the function partial derivative function fxy with respect to y, which is involved in the Picard's theorem. That's why the Lipschitz condition is more powerful than that. So we can easily verify first order differential equation whether these exist, solution of this exist in the given initial condition, and if it exists, whether it is unique or not. So thank you all of you for the first lecture to you, and next I am preparing something which will help. So this is the most first one.